Is the live stream running, Zoe? Okay, great. Welcome everyone to this edition of the McGill Physical Society Colloquium. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building. This year, the colloquia will all be remotely delivered. Sorry, I'm getting echo. Okay, sorry about that. So the online colloquia will work as follows. We'll have a 45-minute talk followed by 15 minutes of questions. After the 45-minute talk and 15 minutes of questions, at approximately 4:30, we will have an après-colloque where all professors will be asked to log off. And non-professors will have the opportunity to talk to the speaker without the prying eyes of supervisors. The recording and live stream will stop at that time. I just should remind everyone that they are being recorded if they're in the Zoom session and being broadcast live on YouTube. So if you prefer not to be recorded or broadcast live, you're welcome to log off and view the colloquium on YouTube. During the question session, you have the option of asking questions in Zoom if you're in the Zoom session or on YouTube. In Zoom, to ask a question, please raise your hand. At the end, not literally raise your hand, but raise your hand icon in Zoom. I will clear all of the hands just before the beginning of the question and answer session. And so there won't be the opportunity to just get your hand up in the middle of the talk. Raise your hand at the very end of the talk. At the beginning of the question and answer session, you'll be asked to unmute and ask a question one by one. In YouTube, if you would like to ask a question, you also have the option of entering a question in the live chat. And now I will pass the baton to Professor Andreas Warburton, who will introduce the speaker. I'll just ask him to unmute. Whoops. I'm afraid I'll ask.
Okay, I think I'm unmuted.
Yes.
Hi, everyone. My name is Andreas Warburton, and I'm a faculty member here in the Department of Physics at McGill. On behalf of all of us, I'd like to warmly welcome you wherever you are, Montreal, elsewhere in Canada, or abroad, to this first Physical Society colloquium of the new academic year, and also the first ever to have this particular online-only format. It's my great pleasure to introduce today's speaker, Claire David, an assistant professor at York University in Toronto in the Department of Physics and Astronomy, and also associate scientist at Fermilab. Her research into the subatomic world is split between collider physics, working for the ATLAS experiment at the CERN Large Hadron Collider, but also neutrino physics. She's starting the new Canadian effort towards the future Deep Underground Neutrino Experiment, or DUNE, hosted by Fermilab. And that, by the way, just yesterday officially became a project under the Canadian Institute of Particle Physics. So we're very excited about that. Dr. David's first degree was a Master of Engineering in Applied Physics at INSA Toulouse in France, specializing in nanophysics and instrumentation. She then switched to physics and obtained a PhD in particle physics from the University of Victoria, working in the ATLAS collaboration. Claire then continued working with ATLAS as a postdoctoral fellow at the DESI lab in Hamburg, Germany. Professor David has a wide range of experience in data analysis, detector operations, and development, and will talk to us today about sorting needles in a haystack and cooling a sandwich, data analysis and detector development with ATLAS at the Large Hadron Collider. Welcome, Professor David. Over to you.
Thank you very much, Andreas. That's very nice. Thank you so much for the invitation. Can you just do a thumbs up if you hear me? Okay, great, exactly. Yeah, thank you. I'm very happy to be here. I mean, to be in front of my laptop, but to talk to you about my research activities in the past year. Actually, this is what I'm going to talk today. This is what I've done during my postdoc, and it was really good years. It was really fun. And behind the lengthy title, what my idea is that I would like to showcase two aspects of the wonderful field of experimental particle physics. Data analysis in one hand, and then what we can do with our hands in the lab in the other hand. So the first part will be on data analysis, and then I will give you an example of the type of hardware work we can do when we build these fancy machines that are detecting what we want to detect. And for this, let's just start right now on the main matter of study. This is half of a pun. Matter is what is all about in particle physics. We want to know what matter is made of, what are the basic blocks of matter. And even if the field is very complex, what fascinates me is how simple the questions are. So what is the universe made of is pretty much one of them. And this is about investigating on the Lego blocks of the universe stew. And not only that, but see how you assemble Legos together. And in terms of the Lego blocks, what's been going on in the history since 1900 is a zoom. We just managed to zoom with technological progress on in parallel. And you can see in this graph that I like is we investigated on different scales of matters, and you can see at the bottom that were different milestones in terms of years. And now we are reaching this concept of elementary particles, something that you can't really cut further. And these Lego blocks, they interact with each other, as I said. And we want to be able to understand these interactions. That's the second things in experimental particle physics. And so far, out of the 4 forces in nature, 3 of them are in the subatomic world playing some various roles. And all of this knowledge has been thought by a lot of physicists over the past century, scratching their head. And what we have in the end is a model. It's called the Standard Model. I'm not so fan of that name. I hope I don't offend anyone in here. But this is the name under which we have the theory of elementary particle physics with, on one hand, the bricks of our reality, particles of matters. On the other hand, the messengers in terms of interactions and what is being exchanged during interactions. And then this particle, the Higgs boson, that's been discovered in 2012, and that was actually based at CERN in 2012, and that was actually fun to see so many journalists in the lab. This Higgs boson is giving mass to the particles that are massive by interacting with them. What I'm going to talk to you about today is on this Higgs boson mechanism, as we say. And on this Higgs boson mechanism, this is really near a puzzle that you can see on this slide. This slide is puzzling physicists, including me, is how come we have all our bricks that are voluminous entities. They have very, very different masses. Actually, if you think of it, these masses are spanning 11 orders of magnitudes. And a picture that you can have pretty handy is to realize is that you have, the electron and the top quark, 2 point-like entities in the descriptions. If one were as heavy as a marble, the other would be as heavy as a big plane. I mean, I put the A380 because this plane was above the southern of France when it was just tested when I was in my engineering school. But that's pretty much illustrating how come we have that. The Higgs mechanism is a proposed explanation, very successful. We discovered the Higgs boson, and so, okay, great. But we want to check that. And how to check this is what I show here on this skeleton of plots. I don't like to show the plots as is. It contains too much information, so I do an autopsy and then I put some parts in it. And this is the main idea behind the research that I've done in data analysis over the past 3 years is we have the prediction. This is the blue line. We have particles. They have some masses, and then associated to them, there is an interaction strength that basically translates how they interact with the Higgs field. We also have the term couplings. This is equivalent. And the measurement in question that I will explain here is we take the particles and we plot them with the mass on the x-axis, and then the thing we measure in terms of interaction strength, how it interacts with the Higgs, we can put some numbers in here. And the idea is to check the theory. Is it going to fall into this linear line? Because the standard model Higgs boson, as described by the theory, is predicting something linear between the particle mass and then the interaction strength. In terms of, you cook a bit the unit, but this blue dashed line is basically the value of the predictive theory. If we are above or below, then something is there that we haven't figured out yet. We talk about new physics. That's a very sexy word in particle physics. But the idea that I will show you right now is this top quark that you can see in here. how to check that it falls on that line or not. And for this, we have to explain to you a bit how we do this idea of coupling things. So the measuring the Higgs coupling to top quark is a very sensitive test to the standard model. That's actually the jargon. And what it means is that if we put this point here on that plot, the mass of the top that we know, and then calculates the interactions strength that we get from the data, the observed entity, we want to know where it lies in here, and that will be a test of this standard model. We want to test that theory to know if it's right or not, and if we have to, some open doors of investigation if we realize that there is a discrepancy between what the theorists are predicting and what the experimentalists are seeing. For that, we've done this in the past with other fermions, other particle of matter, and it's actually easy in the sense that you just produce a Higgs. Okay, not producing a Higgs is not easy, but if you have a Higgs and if it decays into a bottom quark and anti-bottom quark, you have access to the Higgs to bottom quark coupling. That's cool. And if you do the same for Higgs decaying to a tau lepton and then anti-tau lepton, you have access to the coupling between the Higgs and the tau lepton. You quantify how strong they interact or not. And with the top quark, as that guy is very heavy, recall the marble and the plane, we can't have the Higgs decaying into a top and anti-top. That's the quark is too heavy. Game over. So how do we proceed? We proceed with something that is called TTH, which is a production mode. It's a special production mode where a Higgs boson is going to be produced, and at the same time, a pair of top quark and anti-top quark is produced there. And for this is happening if you have some fairly good amount of energy, and then you get that. So this process, a top quark, an anti-top quark, and a Higgs boson, this is what I was looking for during my postdoc. I was trying to get to see this process because that will give a direct access to the Higgs boson to top quark coupling. Cool. How do we do that? Okay. The first thing we need is energy, and quite a complex way to achieve this, you may guess. Our energy provider is the Large Hadron Collider, like one of the most complex machines in the world, and it smashes, protons. This is a proton smasher, and the why you smash proton is just a pretext to have energy. And these protons are accelerated at 99.99991% of the speed of light. A bunch of protons in one sense, in the other sense, boom, flash, energy, great. We can explore at what we said, the energy frontier equals mc squared. And I want to stop here to explain a bit units, because it's very tricky with the units to be a bit mixed up. It says, wow, 13 tera electron volts. Tera is cool for grants on computing infrastructure, like I want terabytes and stuff. But in here, it's not that big if you think of it. Like the 13 tera electron volt is the kinetic energy of a mosquito flying. It's actually 360 billion times less energetic than a blueberry muffin. So why so much money for the Large Hadron Collider if this is to produce such a tiny amount of energy? Well, actually, it's the density. This energy is packed into a very, very, very tiny volume that if you compare with your same blueberry muffin in terms of calories per cubic centimeters, and you convert that, you have then 10 to the power 35 in terms of ratio on how the LHC density in energy is beating our blueberry muffin. So close the parenthesis on the units, but now you have an idea that the LHC is a machine to produce energy at a very small volume in extremely dense amount of energy, and this is what we want. This is how it does not look like. Actually, 100 meter below is not really depicted with a schematic, but it is in the border between Geneva and France, and this would be the LHC ring in Montreal. So that would be tricky to build, but you have now an idea of what it is to have the 27 kilometer circumference ring there. And around this ring are detectors. They are the eyes when protons are colliding and the results of the collisions. And this is the Atlas detector. And the Atlas detector is a gigantic camera. So the people in here, they should not be there. I mean, the security guards will complain. This is our device to see what's happening during the collisions once these protons are being smashed and they produce energy and then particles are created, E equals mc squared. And now the question is, in our quest to see the TTH process, how do we see it in the data? And that's not easy, obviously. It's complicated. First challenge, it's rare. You have 1 in 10 billion collisions that produce a Higgs boson. And then the TTH production is also a very rare process. So you will have to collect a lot of data before you can see something interesting. First challenge. Second challenge, we'll see it further. The top quark, it doesn't live long. It decays super fast. So it's not something that is going to directly reach some detection material. You don't see it. It has vanished already. We will see its decay products. And this is what I want to illustrate in here with you. Here is the first start. You have some proton being smashed. And this is the process that we see. But the process that we see is very unstable. These 3 particles here are going to decay. They are going to decay most of the time into these things. So you see many names, but just don't forget about that. It's just that the next stage of this decay chains, once you have a TTH process in your detector. And the thing is that we don't see that. It's not measurable. It is completely inside the beam pipe. And it's pretty much game over. No. These entities that you see near the edge of that blob are going to decay, and they're going to decay into objects that we see in the detector. And this is what we collect when we collect our data in the detector. We get these final states, it's called, and these are measurable objects. And these are what is going to help us to be able to reconstruct this decay chain that I illustrated to you in here. Then this is basically from what I show in here. I just reduce that blob. We have the TTH process here. We can't really see, but we know that if we have these objects in here produced by the decay products of our top, antitop, and Higgs, then we'll be able to select from all the pile of the collision that we have, those matching these final states. Cool. And this is how it looks like roughly in the detector. You can see the beam pipe is in here. The collision happens in here, and then this is a bit more realistic. Although this is all illustrated, these are schematics. But we have electronic activities and then many algorithms that are reconstructing and identifying patterns to be able to label these as objects. You see the blue cones, this is what's called a B jet, and then you see other cones, this is called a jet. So from the data, we can identify pattern the same way that your camera is identifying smiles. When you see, okay, so far so good. There is a problem, of course. They are processes that are actually mimicking the signal. And I go back to this blob, and in here, what you can see is that's almost the same, of course, but instead of a Higgs, in here you have a gluon. And this gluon is something really massively produced at the LHC, and it's produced the same objects in here. So basically what we are actually facing is 2 processes, same final state. You can see on the left, TH is producing that. And then TT bar, this is the villain. I mean, I'm sorry for those studying this process as the main field study, no offense. It's just that for us, this guy is going to contaminate all our pile of collision to sort out, because it has the same signature in the collision files that we have. And on top of it, this guy is happening 1,000 times more frequently than TTH. It's very frequent to have TT bar even over TTH even. So how can we, if we have a pile of collisions having these objects that are being shown in here, how can we know if we have TTH and if we have TT bar, and how can we just split the 2 and get focused only on our TTH process? This is referring to the title of this talk. We are really looking for a needle, rare needle in a big haystack. For this, how we can get TTH only, we have the trick of quantifying. We quantify. In a given selection, in a given collisions, we'll study the topology and put a number in it. For example, we'll take 2 B jets, and then we will see the most energetic one, and we'll compute the angle between them. Or we will just get all of the energy of each reconstructed object, and et cetera, et cetera. So we have a list of variables that are characterizing our collisions with quantifying elements. Cool. What do we do with this? To the rescue come simulations. The simulations, which I like to depict as a brain and then this casino thing, this is my view of the Monte Carlo event generator. These are tweaked random numbers to then generate randomly some patterns that are mimicking either the TTH signal topology with the knowledge that we have of physics, or the TT bar topology. And all of these files, all of these simulated collisions, we can then study them in terms of how they distribute. Pick a given variable, for example, this angle between the B jet, as I mentioned, and see how the signal simulated is behaving compared to the background simulated is behaving. And with this trick, we can see a bit how we can apply a cut on the variable. Let's say I would take an angle greater than 30 degrees, and I only take the events that are after this angle. I will only keep these events. And what we do is that out of a pile of collisions that we have at first, we enrich our selected pile with signal events over background events. And that's how we can actually extract stuff. We don't do it with one variable. There are fancy technique, and this keyword called machine learning that is very trendy now, is to take these variables, and this is actually the real plot, like the real elements that we've put into a classifier that is going to tweak all the cuts in there and be able to come with a variable that is a score. And this score is an equation built with all of these variables there that are going to compute the probability of having a signal TTH-like collisions or a background-like collision after studying on the whole all of this simulated sample. What do we do with this? I open a little parenthesis in here with a bit more details for those willing to see a bit how the analysis was structured. It was actually a double-stage multivariate analysis. If you have questions on this after, I'm happy to reply on this. But double stage or not, this is a series of computation to work out the best cuts in here to know what to keep and what to discard in order to have as much signal as possible in our sample. And then what we do is that we compare. And when we compare two things: the simulations, our knowledge of physics, and these collisions that are just simulated. They're not really real data, they're simulated, they help us. And then we collect the data and we see if it matches or not. And this is a plot. I told you that I like autopsies of plots, and so I just cut the money plot that we have in physics into the two main things they contain. These plots are two plots. I wish at the start of my PhD, someone explained that to me clearly. There is the number of events we have for a given classification. This is the score. This is in that direction, this is signal-like, and in the other direction, this is background-like. And this is all of the Monte Carlo, all of the simulation. This is the brain with this casino machine. They stack themselves, all of the known process that we have, and also the signal. And this is another plot. And in the end, we see how it compares. And this bin here is what is signal-like, and this bin here is what is background-like. You see, you have our TT bar in here. There are lots of events in here, very little here, and then our red bar of TTH events that could be there. So we compare that. And in the end, when we compare the number of observed data, this number here, the black dot, by the number that is predicted, we can obtain the rates of our TTH process. And if we have the rates of our TTH process, then after some more calculation, we can access the coupling, and bingo, we win. We are okay with that. So this is when it's nice. But then the problem, and this is what I did in my postdoc, and I'm going to skip to be able to really be on time and cover everything, but I promise that if you have any question, either after the question or just drop me an email, you can actually ping me on that, because this is a method that I developed and was pretty interesting. What I would just want to say is that life is not easy. And sometimes in such a reconstructed collision like this, you may see an object and it's not actually the real object. You will see a jet and actually it's not, you will see a jet and actually it's reconstructed as an electron. You will see a jet and then an electron and it's reconstructed into two objects, whereas actually this electron has been produced by the jet. So in the end, you will have something that looks like your signal, but this guy is not a real electron or muon. And you have to take care of that. For the sake of speeding up a bit, I will just mention as possible questions for sure that I developed a method called fake killers. But what I want to actually really say is that usually the fakes in Atlas are handled with the matrix method. This is the method that is just being given, says apply this. Then you will see, you will estimate a bit how much fakes you have. And I got some problems, and sometimes it's good as researchers to just step back and say, wait, can I perhaps investigate other things? And in the end, what I did is to design this fake killer process where I was not even quantifying anything. I was showing that before we select the events that we want with all these cuts, we actually have a very negligible coherent with 0 amount of fakes. So we could neglect them. And then this is pretty making the analysis kind of simpler. So I can come back later. I will jump to, for the sake of having time to cover the rest of my talk, I will talk from the analysis results. And the results are presenting this way. So now you see real plots. You see that what I've been talking about on this TTH, this is where the Higgs is decaying into bottom and anti-bottom. That's one of the scenarios possible. There are other scenarios, and then there is the combination. But what you can see in here is that the rates of this TTH process compared to the rates that the standard model predicts, the theory, is spanning these values, but it's crossing that line. So it's coherent with the theory. We don't have everything that's completely outside. So that is how we should interpret this plot, is that we have these possible values for rates, and the theory predicts in here. So far so good. It was a pretty big milestone, because before the TTH process has not been observed at the LHC. So Carl Jacob, the Atlas spokesperson, was actually pretty cool in this statement, saying that this measurement constitutes a landmark achievement in the exploration of the Higgs mechanism and the interaction of standard model particles with the Higgs bosons. That was a good milestone to have observed the TTH and be able to access the couplings. And now what I want to show you is how it relates with this plot that I introduced at the beginning of this part. Basically, when we have a top quark that we know the mass, how is it going to lie in this in terms of coupling, and is it going actually to cross the theoretical prediction? It does. You can see on this plot, this is the real plot. Now you have it. This is the toe, this is the bottom, and then this is this measurement of the top quark. You forget about this. This is fancy equations, but this is related to the coupling, to the interaction strength. And we have here a linear process. So the standard model of the Higgs mechanism is verified by these measurements that we have. The coupling, usually symbolized by the letter kappa, the coupling is consistent with the standard model prediction. So all of these difficulties make us plot one dot here on this plot. So I want to, this is in particle physics, the discipline is really humbling, because it takes a lot of effort to get like this little dot over there. So we can do further, and as an introduction to my next part, I will show you two plots, the same as before on the left, and then a projection. What would happen if we were having more data? And this is where the predictions, where people were taking the data and multiplying them artificially, I would say, to see how it projects, 37 times more data. And what I want to show you is that in here, what is of interest to us is not really where that point is per se, but to reduce the error as much as possible, to really refine and make sure that we do not have deviation, because here we can't see if we have a deviation in the sense that the error bar is too large. So, but if we really zoom and manage to lower this error, then we'll be able to see if it's actually really lying on that value of 1, this is behaving linearly or not. And if it's not, then this is really the hint and a wonderful door for theorists to investigate further and says, what are unknown processes that are making my top quark not really interacting the way the theory predicts? And this is this new fancy Q, the new physics as, okay, a physics we haven't really explored yet. And that is crucial for theorists to have these hints of, if we search here, we're going to find something interesting. But for this, we need way more data. This is 37.5 more data than what we got in the previous years. And previous years we're collecting quite a lot of data. So this is something that we hear a lot in particle physics. So people really want more data all the time. And we will get them. Not now though, but at some point we'll get more data. And I am actually switching to the other part of my talk, the future. the high luminosity LHC, and this is a wonderful one of these wonderful schematics that we have in particle physics that I find this artistic, I must say. The Atlas Future Inner Tracker. This is the second part of stuff that was making me busy during my year as postdoc, and I'm actually continuing at York University. It's a lot of fun. The Atlas detector will be equipped with a fancy tracker that you see pictured here. That is going to be for the years 27 onwards, what's called the high luminosity LHC. High luminosity means you have way more collisions at a given rate. Instead of 2 to the 1034, forget the unit, we're not just comparing. You just increase it to 7.5 to the 34. This is this increase in luminosity that is going to make us pile a way lot more collisions to analyze. We had 139 inverse femtobarns right now collected by the Atlas detector. So one inverse femtobarn, this is approximately 100 trillion proton-proton collision. This is how big the pile of collision to analyze is, right? But here in 2027, we'll have roughly 300, but with the high luminosity LHC, this will climb up to 4,000. That's a lot of collision. That's a lot of rare processes that's going to be less rare, and then we'll be able to analyze and refine our theories. And for this, there will be some challenges because once you make more violent collisions, you make more mess. This is the mess we have right now. 7 centimeter zoom of the beam pipe. If you put your eyes, don't maybe, but if you put your eyes near the interaction point, you will see so many tracks, and only some tracks are actually what interests you to analyze, and the rest is some noises that needs to be discarded and cleaned up. At the high luminosity LHC, we will have that mess. Instead of having roughly 60 collisions, one we want, 59 we don't want, here we'll have 200 roughly collisions of this proton-proton per bunch crossing. That's going to be some challenge in several aspects, actually. And for tackling these challenges, we will have to upgrade. So this is necessary to be able to improve the detector performance and also to make sure that nothing is going to get destroyed, because there will be really high radiation levels and you want your electronics to work properly in that harsh environment. And for this, the current tracker, which is a device similar to a camera, but it's just to reconstruct the tracks of charged particles. The current tracker that we have right now is going to be fully replaced, like removed. A new one is coming, and this new one is called ITK, the Atlas Inner Tracker, and it will be fully composed. It will be a silicon detector, and one composed in pixel in the center, and then strips, which is an elongated pixel, to be comparable to that. And it has 2 parts. It has a barrel, like it has the shape of a barrel, and then some end caps, which are the discs that you can see in here, okay? And this is what is being built at the moment. And it has several specs, a lot of challenges, 3 mains, I would say. First, it needs to be able to decipher all of this mess in here, to be able to reconstruct only the tracks we want. So that's advanced sensor technologies and electronic. And then it needs to be radiation hard. That is to say, things need to work even if the radiation levels are really, really high. So there are special chips being designed at CERN on that to be able to ensure that it's going to work okay. And then it's going to be way more things to manage just in terms of channels. We'll have 7.5 more channels. So that's a lot of challenges on the data acquisition side. Among all of these channels, what I focused on and why I want to present you the sandwich, the second part of that talk, is on the temperature. The sensor, the silicon sensor at the base of collecting the signal, they need to be cold to function. If they're not cold, they won't function. So that's the main thing. And with all the other aspects that I introduced to you, the radiation damage and then the way more channels, they will be different pouring system and then higher currents in the end, that will translate into more heat. So my duty was to be able to assess how the structure holding the sensor was dissipating heat correctly, so that the sensor will be put in the correct temperature range to be able to work the way they should work. And here is the sandwich. The structure that I've been working on looks this way. This is, the technical name is the petal in our jargon, but I call it a sandwich and you will understand why. There are discs that compose this end cap. Recall that this is like 2 meters. This is something like 2 meters diameter, even more. And these discs, the beam pipe will be here, are populated by this sandwich. And the sandwich is nothing more than the structure where the sensor are glued on it and they hold the sensor in it. And if you zoom in a bit, you can see how it looks like. I will detail a bit the components. But what I want to show you first is how it looks like the prototype. That's something that I took this picture when I arrived as a postdoc, and I was just so happy to touch a part of Atlas because I've been having a PhD only touching keyboard. And I was doing some soldering in here, and I was just very happy to be able to at least get some hands on. This is the prototype where the sensor are actually these pieces in here that you can see glued on some fiber plates, and there are some electronics on top of it, and all of these chips in here are collecting the signals from the strips, and the strips are radial in here. They're actually pointing to the center of the detector, to the beam pipe. So with this prototypes in here, you can see how it looks like once you explode it. So it's just some carbon fibers and then some bus tape and then the sensor on top of it, a lot of glue. And if you see the cross section in here, there is a cooling loop that just goes through the whole thing in here and has these little, this is the cooling loop cross section. And it's going to get the heat of the sensor just put back in here to be able to dissipate the heat as much as possible. So it just goes here and then go all the way through here. You can actually see the cooling loop. And
you have 10 minutes left.
Sure.
10 minutes.
And the mission that I had was to measure the performance of that sandwich to see if it was cooling the way it was supposed to cool. And the most important question in here, like cutting the problem into different parts, the more important question was actually to make sure that the sensor measured on the temperature measured on the surface of the sensor was actually matching the ones simulated, to make sure that we understand what we are doing. So it was crucial for the design validations, and this was the mission in the lab at DESY to be able to assess that. And for that, we equipped the petal, the sandwich. So you can see a frame where the sandwich was attached, and then all the electronic was monitored in here. And the thing is that we're using an infrared camera. And an infrared camera is very nice, you make very nice video, you can play a lot with it. But silicon is the worst, one of the worst materials you can have to do some infrared tests because it's a poor emitter. It just reflects everything. So for this, we just painted it black. So then it was just coated with some very high emitting spray. So the spray would be the same temperature at the sensor surface. And then this is what we'll record with the camera. And we had a chamber in here that was completely dark inside, so that we were cutting a lot of external heat source that will actually damage the measurements. Even the camera was oriented this way, because if you put the camera really facing the object of study, you get all the heat of the camera bouncing back to you. So you get actually the mirror image of the camera. That's the joys of infrared techniques, where you have to think differently with radiation to be able to have a good measurement. So the camera was actually having a little angle, so then the heat was just bouncing it back, and we were not collecting the what we call the Narcissus effect in terms of heat. And this is the setup that we got. My students really liked New York, so he just piled everything up. Perhaps it's not really the most secure setup, but what I want to say in here, I think I was, a bit, I think my colleagues were mocking me, but I was trying to paint this petal in here using the chamber to be able to paint it black. And what you can notice is that the chamber can rotate. You see it's horizontal, and then it was actually put vertically because we wanted to measure the performance in different orientation. It was crucial because if you have the coolant just going this way, it's different than if the coolant is just climbing up against gravity the other way. And as the sandwich are going to populate all of the disk in different orientations, you see this is vertical, this is horizontal, this will be vertical the other direction. We had to compare this. So that was the first test we did. And there is an Easter egg on this picture. I'm actually in here with the flash, and this is my hand saying victory. We were measuring, okay, everything was smooth. And the first results we got are depicted in this thing in here. We were measuring, this is a picture of the temperature distributions, and when the coolant is in here, you can see the cooling loop because it's actually at the lowest temperature. And we were seeing very little difference compared to the margin we have, 2 or 3 degrees. And this is understood. We were seeing very different changes between the horizontal, vertical, and vertical the other way direction. So we were pretty pleased with that. Last but not least, the last measurements I want to show you is that we compared with simulations. So we had some folks doing some simulations and predictions, and then we were putting our plots nearby. And it was fairly nice. This is how we passed the committee review. The distribution between the simulation and here are pretty much matching what we had from the infrared measurements, and everything that is different were actually difference of designs that were completely understood. So we were happy, the reviewers were happy, and we were celebrating. So that's the first money plot that got us to actually have an excellent agreement between the simulation and the experimental measurements, and the design could validate it this way. Of course, I am trying to skip details to put things a bit general in here, but feel free to ping me during the question for some more details on this. We played with evaporative CO2. It was a lot of fun. A bit dangerous at times, but a lot of fun, and no one died, so we're good. I'm here to my summary, and I think I'm on time. I hope you enjoyed this little tour between the two aspects of the joys of experimental particle physics. On one hand, in the data analysis, I introduced to you the fact that in collider physics, we smash to probe. That's what we do. We very brute force, we smash protons, and then we can probe the universe. And how more specifically, you could see the example of the TTH analysis as a test of the standard model to check if things interact at the strength they are predicted or not, and see a bit of the tools that I gave you on how to assess and how to extract the signal over background, which is the game that we play in data analysis. And of course, now you have a sense that if we want new physics, if we want to get something interesting, we always need way more data. We'll have more data, and Atlas will be equipped with this very fancy machine that is an inner tracker, and that is a beautiful machine. It has a lot of challenges to tackle, and measuring thermal performance is one example of the very fun you can have doing some hardware and building a test stand, collecting your own data and seeing the results and being happy about it. It's frustrating at times, I tell you, I will not really lie, but it's fun over the long terms, and it's very gratifying. This being said, there is still puzzling questions. You can see this graph. Yes, even if this guy in here, the top, is really correctly falling into, for now, the prediction of the standard model, we're still puzzled of why we have so many different masses. And look at the neutrinos over there. This is even more puzzling. And I can't resist to the fact to say that, yes, I am starting the effort on June. And I am really, really, really happy to talk about this future experiment that is going to answer Nobel Prize winning questions. But for this, if you want to invite me for another colloquium, I will be very happy to prepare something for that. So thank you so much. I think I'm a bit in advance, but then there will be a bit more questions, and that will be actually cool. I welcome, so questions, not perhaps too big, but I hope you appreciate, and looking forward to interacting with you in a more casual way.
Thank you very much, Professor David. I think many people enjoyed that talk. Please give your appreciation with clapping hands if you can, if you know how to do that in Zoom or on YouTube. Say something in the chat about how much you enjoyed the talk. I noticed the chat was going a little bit. There was this guy named Koish who was really excited about some of the analogies to Timbits and blueberry muffins, at least. Yeah, no, a lot of people in the chat are saying good things. So I guess I'll kick off the question period with a question from YouTube. And so there's a question, will the HL-LHC also increase the energy of the collision in the center of mass, or just the luminosity?
Oh, I think it will go to 14 TeV. The increase in center of mass is something pretty much designed. You can't really go superly further than that. Yeah, the nominal design is 14 TeV, and this is what I've been heard of. I perhaps don't get the latest news. I don't want to state something that I'm not 100% sure about. This is pretty much given. What is being done right now into the collisions and this luminosity is to have ways to really increase our stack of stuff to analyze. And this is crucial. Yes, if you get this higher energy, you probe higher masses, but only on the given energy range, just having a huge pile of data, then for us, what we see is that, okay, the rare processes are going to occur in a rate that will be a bit pleased. Otherwise, we'll just have 2 or 3 events and we'll be a bit sad with this. So, yeah.
Okay, thank you very much. Anyone in Zoom who wants to raise their hand, please raise the hand icon if you want to ask a talk or ask a question. We already have one, so I'll unmute Jim Klein. Jim, please go ahead.
Hi, that was a very, very nice talk. And I just had a couple questions. So one of them was, why do you prefer the 2-jet 1-lepton final state to the dilepton? And the other one is, what's the lowest quark or lepton do you think you'll be able to probe its couplings through Higgs decays by the end of the LHC?
These are difficult questions, but again, okay. There were also definitely all the channels are considered in the TTH topology. Of course, you could see in the results that I've been talking that there were several lines of several channels. Yes, there are also 2 leptons and there are also multi-leptons. I ended up working for the 1-lepton channel. And these are the given tricks that you use to be able to extract the signal in the correct way. But yeah, there is also a sensitivity with the dilepton channel, and this has been also processed, and then everything is being combined together for this. So right now, I think the multi-lepton is getting a lot of sensitivities on this. In terms of your question, what is the lowest quark or lepton by the end of the LHC? You mean high luminosity LHC or just run 3 or so? But to stay general on these questions, I would say that everything is tricky. For example, even if the TTH that I presented, the Higgs decaying to BB, this is done 58% of the time. This is pretty much a frequent decay. Even this, you let enter a lot of noise as well, and then this is super hard to actually extract signal over background. For the I know that the muon, the Higgs mu, this has been discovered lately, and this was quite a challenge. So they really needed a lot of data for this. So I would say that most of the measurements so far, as soon as you put more data, they will be refined. You will always gain on this. You will always gain to refine your measurement with more data. In terms of what is going to be hard, definitely on the plot, definitely the Higgs mu is going to be challenging, and but it's also going to be a challenge to get to extract the signal on the top quark to reduce the error as much as we can. For the TTH analysis, there are lots of issues in modeling some of the main background, and that's going to be a phenomenological barrier in how we can improve the modeling on the samples that we work with, for example. So
thank you.
Everything would be hard. We'll have to scratch our head too.
Okay, thanks. Jim, if that's all, please go ahead and mute yourself again. Just to let people know, if you want to raise your hand, it'll bring you to the top of the participants list. Don't lower your hand until you don't want to say anything anymore. I won't be able to find you in the participants list easily unless you have your hand raised. But we have another question from YouTube. So the next question from YouTube is, apart from colliders, can we extract information about the top quark in the universe? I mean, for instance, in gravitational waves or in the CMB?
I will say the Joker, I don't know for sure. There are going to be studies that are bringing up some insight. For example, in colliders, there are different types of colliders that are going to be not necessarily proton colliders, and so. But in terms of gravitational waves and interferometry, I would say this is where my expertise stops. But I would be happy if someone in the audience knows how this can complete in terms of to complete the picture on that. But directly speaking, I'm not aware of what could bring some more insight, especially on the TTH. Theoretical advances for sure. Once we have simulation that are better matching the reality, this will help for sure. But it's still in the part of particle physics phenomenology. In cosmology, no.
Okay, so we have still up to 10 minutes for questions. If people have more questions from YouTube or from the Zoom session, please raise your hand in Zoom. There's a raised hand. Ask to unmute. So this is Shreya Saha. Please briefly introduce yourself and go ahead and ask your question.
Okay. So I'm a PhD student with Atlas, actually. So I had a more specific question about the fake killer. Just in the one you mentioned about in the TTH analysis. Like just a rough idea as to what the main idea was behind.
The main idea behind the method of fake
yeah,
killer?
Yeah.
Yeah, okay, sure. Well, thanks for asking, but at least I know there is one person interested. In terms of this, the fake killer, the idea was the following. Do you see my slides on a simplified plot? The fakes, the mis-reconstruction, if they are somewhere, they are actually in the data, because the simulated collisions, they simulate what they need to simulate. So it's very rare. It still happens that some stuff needs to be reconstructed as a jet, and actually it's reconstructed as an electron. Mistake, problem. But these are mostly going to be in the data that you will collect some fakes. So the idea in the study that I conducted was to state that, okay, I would say that all the different data minus all of my Monte Carlo simulations, this will be the fakes, like an extremely conservative approach, okay? And I start from this, okay, we have pure fakes, and now we are going to compare with different isolation working points. So I explained what is isolation for working points from people not really knowing this. When we reconstruct our collisions, when we see all of these electronic activities, we look for patterns, and then we see a jet of particles, and we have an algorithm that's going to run and say, okay, this is a jet, this is an electron. So these algorithms, they can be tweaked, they have parameters. And one of the parameters of an algorithm is the isolation. It says, okay, I see some electronic activity in here, and it's pretty condensed, and then everything is silent around my code, so it's pretty isolated. This will be a highly isolated working point, let's say. But we can run another algorithm that is a bit laid back and says, I see some electronic activity and some mess around, like some stuff, I don't care. I will still state that this is an electron. So we were comparing different isolation working points, and I tried to picture this a bit, still putting some technical word, perhaps if you're in Atlas, you know, like no isolation, it's like we don't really care. And then the gradients, which is the name of this isolation working point, it's a reconstruction algorithm that is really going to check if we have an electron and we have nothing around it. There is no electronic activity that is going to parasite the whole thing. And what I did is that I did this plot. So you recognize from the colors that what is in red is this pretty clean algo reconstructing my object. And then what is yellow is like we are laid back, we let a lot of dust in. And the variable MTW is linked to the W boson mass. So the W is one of this product decaying into in our scenario, an electron or a muon. And all of these events are basically peaking pretty much at the mass of that particle, around 80 GeV. But below that, we know actually that this variable is containing a lot of mis-reconstructed objects, that there are a lot of errors in below 80 GeV. And what we can see, and I focus on the ratio pad. The ratio pad is this difference between data and MC. So my crazy overly conservative estimation of fakes that I compare with the nominal MC. That's just the estimation. So it will be this relative, like how big is this compared to that, the simulation. And this and in here we can see that
for the points that are having no isolation, we have something pretty big, right? And then it decreases a bit once you isolate a bit more. And then for these two guys, we realized that we have something pretty steady after 80. And then what we have in here is perhaps not really due to the phase. There would be perhaps a more drop that we will see if we have something a bit more isolated. But what I could show is that around, and this is one plot, but there were many other plots to check in many other regions. What I could show is that once we select the analysis sample matching or signal region, or just the series of cuts to select our collisions, we were in the zone that basically the isolation variables were playing almost no influence in terms of the discrepancy we had between data and Monte Carlo and the simulated. So once you have something that is pretty flat in here, you can actually state that actually the amount of fakes are pretty reduced by these isolation variables. And once you only collect in the end to compute your results, you only use something such as gradient, which is pretty much a clean reconstruction algorithm, really checking that no one is around or electrons or muons, then you end up having something fairly independent on the fakes. And then of course the discrepancy that you have is due to other things such as mismodeling, such as the fact that it's very difficult to agree completely with the Monte Carlo, and then this is tweaked by some fitting procedure later on. But it was not purely the fault of fakes that were killed right at the entrance of our analysis by the cuts that we are putting. And one of them is the simple use of that reconstruction algorithm that was cleaning our events enough to make the fakes negligible. I can point to you to more Atlas slides thoroughly explaining this rather than these improv right now, if you want.
Okay, thank you. Maybe you can go into more detail in the après colloque session. I don't see any more questions from Zoom or from YouTube, but yeah, so Shreya says, thanks, Claire, that's super useful. I'm afraid she was muted, so she didn't get to say it in person. So definitely people appreciated it. So if there are no urgent questions, we're in the last 3 minutes of time. I think maybe this is the time to thank Professor David again for a very nice talk. I'll ask all the people on YouTube and all the people in Zoom to come again next week, Friday at 3:30 p.m. For a talk by Nima Arkani Hamed from the Institute for Advanced Study in Princeton, New Jersey. And with that, thank you very much for your attention.